All right, let's talk a little bit about an aldol condensation where two aldehydes, two of the same carbonyls, are actually reacting with each other. So what's going to happen is one of them's going to be the nucleophile, one's going to be the electrophile. We're going to draw in our alpha CHs. So I want to make that one our, it's going to be deprotonated. There's just some carbon numbering here, even just some simple 1, 2, 3, 1, 2, 3, 4. Just to keep track. So carbon 2 is going to be my nucleophile, I'm going to deprotonate there, and carbon 3 is actually my electrophile. So we'll make my enolate. Again, basic conditions. Make that enolate. And so deprotonation, things we've seen before. Get that enolate made. Now carbon 2 is a nucleophile. Got a negative charge. And what it's going to do is going to react with carbon 3 in a similar way you've seen these addition reactions lots before. The only thing different now with these aldol reactions is actually this nucleophile is just a lot more complicated. Like you just got more pieces where carbon numbering becomes really much more important. But it's a lot of the same mechanisms over and over again. So we do that first step, addition. All right. Okay, so come back. I've done the addition. Again, you can see this kind of it becomes unwieldy. It looks a lot more complicated than it really is, right? This is a simple mechanism. If I just wrote this as nucleophile, we could easily do this, but this is just a really complicated nucleophile where numbering your carbons really starts to matter at this point. One of the other byproducts I didn't draw initially, of course, we made water, right? When the hydroxide deprotonated the alpha position, made our enolate, which attacked our, so that's our nucleophile, that's our electrophile. So what's going to happen here is actually this O minus, right? We have tetrahedral intermediate, and every time we make a tetrahedral intermediate, we ask ourselves, do we have any good leaving groups? And with these aldehydes and ketones, right, these aren't carboxylic acid derivatives, we don't, right? We have a hydrogen, a carbon, and a carbon. We don't have any good leaving groups. So what's going to happen here, we're not going to react anymore. We're actually going to deprotonate again and regenerate OH minus. So another deprot and regenerate OH minus. Okay, so here we are. We've done the deprotonation, redrawn this, and this is that aldol reaction, aldehyde and all. A lot of times what can happen, what's not going to happen here for a couple reasons, this is at a cold temperature, but also sometimes what can happen is you can actually do an aldol condensation where you make a pi bond here, right? You make a conjugated alpha beta conjugated system, right? Resonance is always good if we can do it. But the problem here is if you look at carbon 2, there's no hydrogens left to deprotonate. So we can't do an E2 type elimination here. So we're stuck just with the aldol without a condensation. So this is the final product. The difficult part is recognizing this nucleophile, making sure we're numbering our carbons well, and not losing any atoms. So this is a classic aldol reaction without a condensation. So aldol reaction, no condensation.